so I can introduce things properly. I'm Carl Axelson, the president of the Watershed Council, the Pine Creek Watershed Council, for those that I haven't met. And I'm going to introduce Kirk in just a second, but we're here to... Really? Yeah. I need this? Okay. What I wanted to introduce, first of all, John Mullen. For those of you who haven't met John, park manager, not only this park, but thousands and thousands of acres around us. And Gary Bagensticker in the back, who's president of the Friends of Tryon Creek Park, or Friends of Tryon Creek. And I think everybody's notable, but those two are the ones we'll make mention of. I'll just say in introduction that for decades now, thousands and thousands of volunteers and many, many different organizations have worked to enhance the ecological health of this creek and this park and the entire watershed around it. And what we're going to hear from Kirk Schrader tonight is information that I think will help motivate us, that'll help us understand why we're doing the work and why success is so important. And we are achieving success. I'm not going to say much more than that. Kirk has worked for over 40 years as a fishery biologist and has recently retired from Oregon Department of Fish and Wildlife after 35 years. It's not enough. In the last 16 years, he helped design and conduct research studies on adult and juvenile Chinook salmon in the Willamette Basin, with a focus on understanding the complex freshwater life history of juvenile salmon. I'm just going to quick aside. I've learned in the last year working on a couple of projects that juvenile Chinook are really, really important to everything we're doing. And we think a lot about coho. This is historically a coho stream, but the juvenile Chinook and the ability to find rearing habitat is really, really important to an awful lot of people, and there's an awful lot of money involved in that, so learning more about it's critical. That's my aside. With a focus on understanding the complex freshwater life history of juvenile salmon. Results from these studies and from other collaborative research with OSU and the University of Oregon scientists have been used to identify and develop conservation and recovery actions for Willamette Spring Chinook, which is key to what we're all about. So, Kirk, all yours.
Okay.
And, well, thank you all for coming too, by the way. I forgot to say that.
Yeah, thanks for coming out tonight. I've got to say this is probably one of the better venues I've been at. I'll probably get distracted, watching for birds and stuff here. Normally it's just an enclosed room, so it's kind of refreshing to actually have a view. So I wanted to acknowledge the collaborators on this study. Lou Quitman's down here in front, and he's sort of taking over for where I left off, and hopefully not too big a mess, but as long as he stays away from my old desk, I think he'll be okay. So go ahead. So I just wanted to kind of go over the general life history of the Willamette Spring Chinook. If we start here with the peak migration at Willamette Falls, we're sort of in that peak period right now where the adults are going over the falls. The thing about spring Chinook adults is they come in early, and so they actually need some pretty cool water to hold, because they hold for several months in fresh water before they actually spawn. They spawn in late August into October, and then from that period the eggs are in the gravel for anywhere from December. You might see some early hatching in areas that are a little bit warmer, but in colder areas it may be as late as April before the eggs hatch. They'll rear for anywhere from 5 to 15 months in fresh water before they actually go to the ocean. So they can spend a lot of time in fresh water. They're not like fall Chinook on the coast, which may spend as little as a few weeks before they actually hit the estuary. Finally, from what we know about their ocean migration, they tend to go to the North Pacific, and our fish are about 4 or 5 years old in general when they come back. So they spend 3 to 4 years in the ocean. And today I'll mainly just be talking about the sort of the juvenile life history aspects of our work especially. Okay. So you're all mostly familiar, I'm sure, with the Willamette Basin. The spring Chinook really, historically, have always just spawned in these east side tributaries, the ones that come out of the Cascades. Part of the reason for that is, as I mentioned, they do need cold water to hold over through the summer, and you just don't get that out of the streams that are coming out of the Coast Range. It's the most populous valley in Oregon, certainly. I think I've seen some estimates where maybe 70 to 75% of the entire population in Oregon lives within a few miles of the Willamette River. So it's definitely a very populous river. One of the big drivers in terms of their decline has been the construction of flood control dams in all of these spawning tributaries. And in some cases we've lost, like in the Middle Fork Willamette, because the dam, Lookout Point, Dexter, and Fall Creek dams are so low in the basin, we've lost almost 95% of that historic spawning and early rearing habitat. So the dams have had a really big impact, especially in terms of the spawning locations and the early rearing. The other big driver is just, as I mentioned, lots of people living here. So in terms of trying to fashion restoration measures like for example, maybe changing flow management out of the dam so that we could increase more natural flooding, we're going to be constricted by the fact that we have all these population centers. So what we've really done is kind of constrained our ability to manage the river with more of a natural flow regime, and we'll have to work around that. I mean, certainly, we're not going to be advocating that Eugene, Springfield, or Salem be exposed to floods every year. Some of it may happen. Only about 30% of the entire watershed does have flood-controlled dams on it. So I think in some cases we sort of have this false sense of security that we're all protected from floods because of the dams. Historically, the Willamette was used a lot for salmon fishing, both by the Native Americans and then the early settlers. And you can see that back in those days, there wasn't much of a catch limit. I guess this is what's known as a boatload of salmon, but this is actually taken somewhere down near Oswego, that photo.
That might be the confluence.
Yeah. But the river is also a big driver for water power, so a lot of industry was sited on the riverbanks. The river was a highway, so it was used for transportation. And of course, because everyone likes to live along the rivers, this is what you sort of end up with. Here's the Portland area where we've really just kind of went right up to the banks of the river and constructed seawalls, and there's not a lot of natural habitat in this area. So we live close to the river, but the rivers don't always behave the way we want them to. It looks like in the old days that they were a little more innovative maybe than we are today. When the rivers rose, they just decided to raise their sidewalks and went along with their daily business. So because the rivers don't respond the way we want, we've have developed all sorts of techniques to make the river behave the way we want. We went, the Army Corps of Engineers had a big channel clearing project in the late 1800s where big log jams of cottonwoods were removed from the river, which then also caused the river to start unraveling. And part of that response was then to, riprap, use a lot of revetments to try and keep the river in its bank. And You might not be able to see it real well. This is in the Salem area where instead of rock, they used old car bodies for part of their bank armoring. And of course, one of the big responses is the construction of dams to try and keep the river, more confined. So when we think about the Willamette, oftentimes there's sort of two views. And when we first started our project, the prevailing view was really that the Willamette is just sort of a migration corridor for juvenile Chinook. And part of that, it's more of a technological approach because, we had the dams and it was felt, well, we can use the dams to control the river. We have a lot of hatcheries that were actually built to help mitigate for the loss of habitat from the dams. So the hatcheries were sort of looked at as controlling fish production. And really, I think partly because of the big pollution problems that we had in the lower river in the 40s, 50s, and 60s, the Willamette was really viewed as sort of a bad place to hang out. And so the response would be then to, as part of the management of the river, would be to, let's basically take fish, flush them out of the spawning areas and get them downriver. And this is, if you were going to model that, this is sort of what the model would look like. Here's, you use your reservoirs as sort of your handle and get the fish out as fast as possible. The alternative is you look at it, the river more ecological. You try to restore some natural flows, natural temperatures. You rely more on natural spawning and rearing. And with more diverse river, you'd expect to see more of an expression, the full expression of life histories. And in that aspect, the driving management might be that to restore the complexity of the river and also to restore habitats so that they're connected to the main river and they're accessible to fish to use. So I'm going to be talking mostly about the juvenile life history, and this just gives you a little bit of the terminology that's often used. The egg incubation phase we haven't really dealt with in our project, but as soon as they start hatching, oftentimes the fry will come out of the gravel, and they may even start moving before they've actually fully absorbed their yolk sac. So when they first come when they first hatch from the eggs, they're actually relying on that yolk sac. They're absorbing that, and that's what they're using for food. And then they start transitioning into getting food from the rivers. So occasionally we do actually see fish of that stage quite far downstream. It's actually pretty amazing how far a fish that's just out of the gravel can move. Most of the fry that we catch are actually, what we call buttoned up. They've already absorbed their yolk sac and they're actively feeding. As they grow, there's a stage that we kind of call the par stage. These are fish that they're not at the stage where they're ready to smolt and go to the ocean, but they're growing, and they're called that way because of these par marks on there still real visible. And then as they get real silver and they're starting to make the physiological transition to be able to live in salt water, then that's their smolt stage, and at that point they're actively migrating to the ocean. So in our study, we capture juveniles at all stages from fry to par to smolt. We use any number of seines, some pole seines, a little bit larger ones. In this example up here, we actually put a seine in the river, and then we use snorkelers to actually herd the Chinook into the seine. And then when we're on the main river, we're using a big net, 150-foot seine to basically sample very large bodies of water. And our main, at least for the larger fish, our main sampling technique to track the fish is using what's called a pit tag. It's the same type of tag that veterinarians put in dogs. It's a little passive tag, and if it passes through an antenna, then that tag gets activated and it sends a code out. And so where we're able to monitor the fish is as they move from the upper Mackenzie River, for example, they go through, this is Lieberg Dam, and there's a bypass that sends the juveniles through this bypass and through one of these pit tag antennas. So if we've tagged fish in the upper Willamette River, we can tell at what point it's gone downstream. And down in this part of the river, at the P.G. Sullivan plant at Willamette Falls, we also have an antenna. And we can, any fish that's directed over through their bypass and passes through the antennas, then we can tell, for example, at what size we tag the fish and exactly what location and what date we tag those fish. Because it's a passive technique, we can't actually tell how large the fish are when they leave, but we're supplementing a little bit of sampling by trying to get our hands on fish at this point. So we've done a lot of our work in the Mackenzie Basin, and part of that is because it's really, for the upper Willamette, it's really the only intact, or mostly intact basin that we have. These areas here are still the historic spawning areas that fish have always used, and they still have access to those. They're cold water areas, so we can kind of use the Mackenzie almost as a template. We can kind of see, what would have fish behave like in more of a natural setting, and hopefully we can use that to then expand to some of the other basins and say, if this is how fish are behaving in more of a natural setting, then what do we have to do to some of these other basins in order to try to get conditions at least maybe close to that. One example is adults are now being put above Cougar Dam, and in an attempt to maybe reconnect some fish with their historic spawning and rearing habitats. So there's another big study going on in the South Fork. So we sample fish in this area. We also sample fish after they've migrated down into the lower Mackenzie, and then in the Willamette, basically all the way down to just above the falls. And more recently, there's a new study that Metro is funding, where a little more sampling is going on down around Sauvie Island. So hopefully we'll gain a little bit more knowledge about some of the fish use in this area. So one of the things when we first started compiling information about fish migration, from the upper Mackenzie, what we saw, which was a little bit surprising, was this really big fry migration. Shortly after the fish emerged from the gravel, we'd see large numbers of fry moving downstream. And then later in the fall, another big pulse of fish moving out, usually starting with the first fall rains. And then surprisingly, for spring Chinook, oftentimes it's thought that the spring smolt, or the fish that are a little bit over a year, are sort of the primary migrant. And at least in the Mackenzie system, those fish appeared to be a relatively small component of the active migrants. So our questions really sort of centered around what these fish are doing. Where were they going? That was one of the main questions we asked in this study. So first I'm going to deal with those larger fish, the fall migrants and the spring smolts. And we tag those fish as they're moving past Lieberg Dam. And then this is the time at which they were detected at Willamette Falls. So once they're at Willamette Falls, we're fairly confident that that they're on a pretty active migration, and either going to spend maybe a little bit of time in the lower Willamette or in the Columbia, or heading on out to the ocean. So the fish tagged in the fall, yeah, we did see some of those fish that tended to keep moving and head out of the Willamette. But almost 70% of them spent some time, probably spent the winter in the Willamette and didn't go out till the following spring. So that told us, at least for that component, that the Willamette was a pretty important rearing habitat for these fall migrants for the winter. And the spring smolts, as we suspected, tended to go out fairly quickly, but even some of those took up to 3 months for them to work their way down from the lower Mackenzie down through the Willamette and on out. So even those fish are spending quite a bit of time probably hopscotching their way down the Willamette. The fry migrants were really kind of an interesting group for us to find. Again, we found that shortly after migration, or shortly after they emerged from the gravel, we'd see these migrations starting. In the Santiam, they start a little bit earlier because both of those systems have dams on them, and the dams tend to release water that's a little bit warmer, so those fish develop a little faster and emerge from the gravel a little faster. So we tended to see, these fish migrating a little bit earlier, but really, continuing their migration down into the Willamette. And for the Mackenzie, their migration started a little bit later, but they, woo, okay. That starts a little bit later in the Mackenzie, but again, they tend to just keep on moving, and by the time, and then more recently, we've noted that they don't just move into this area, but we've seen continued migration over the falls into the lower Willamette and possibly even into the Columbia. So by March, what we've seen is really, this whole Willamette is populated with juvenile Chinook that have migrated out of the spawning tributaries. And here's an example of a group of fish that we sampled in March. Because of the Mackenzie from this, up above this point, the Mackenzie is really the only major spawning tributary. So these fish had to have come from the Mackenzie. And there's quite a range of size even by March. So these are probably fish that got down maybe in January. And these are probably fish that just recently arrived. And you can see how much growth that these fish that arrive early obtain. And that's in the wintertime when you don't think of the river conditions as being that great for rearing and growth. But the Willamette is warmer and continues to be probably a pretty productive habitat for these fish to grow in. What we have found is that most of these fish that are rearing in here migrate out that first summer. So they tend to reach a size at which they're capable of smolting and going to the ocean. And we do have, as I'll talk about later, we do have some fish that hold over, but we do see a lot of these fish moving out within a few months. Going back to then these fry, here's just a little bit of information about sampling that we've done recently down in the lower Willamette. We tend to see fish, their first fry showing up anywhere from December to January down here, and peak catches in February and March. So these fish are coming down, they're holding up. This happens to be around Clackamas Park, probably anywhere where there's some shallow water, maybe a little more natural habitat is where, anytime we kind of drag these little pole seines through, we'll find fry in some of those areas. Another important aspect, which may be more relevant to places like Tryon Creek, is that we have seen that in the wintertime, juvenile snook will move sometimes quite far out of the Willamette into other tributaries. These are just a couple examples of a juvenile chinook being found in the Corvallis area, 14 miles from the Willamette, following Muddy Creek up and captured in this really small tributary here. Another example is this quite, what you think of as fairly insignificant little stream where several juvenile chinook were found up there, and they probably tend to just kind of go out during high water and keep going, rear, and then probably as the water drops, then they move on out. In both of these cases, the fish would have had to gone through several culverts to access these areas. So passage, even though it may look like kind of an insignificant stream, and in some cases the only time they run water is in the winter time. They may look fairly insignificant, but as long as fish have passage, they will access these types of waters. So what we've seen, though, is that as I tried to demonstrate with that one photo of all the fish, the rearing conditions are actually quite good in the Willamette. And this part here is fry that we sampled in both locations, and they start off pretty much the same size, but it's not very long before the fish that are in the Willamette really start diverging and putting on significant growth compared to those in the upper Mackenzie, which is considerably cooler water. And there's probably a point at which a fish reaches a certain size and it's still early enough in the summer that triggers that smolting behavior. So if they're large enough, soon enough, they will probably go to the ocean. And the difference in the growth is such that these fish that are in the upper Mackenzie really don't reach probably that threshold size until fall. So it takes them quite a bit longer before they're actually ready to start, at least some sort of a migratory behavior. And then this just kind of shows how we can see the signature of migration between the two sampling locations. So this dotted line is fish moving out of the upper Mackenzie, so they're moving out of the spawning areas, rearing in the Willamette, and then we see this big peak here with what we call the sub-yearling smolts. But some of these fish are also hanging on and migrating to the ocean later. Here's that fall migration out of the upper Mackenzie, and there is a little bit of a pulse there, but not as significant as the sub-yearling. And then here's the spring smolt, and we really don't see that kind of signature in the Mackenzie. So this group is really composed of probably all three of these other groups. Fish that are spending the summer, they're going to stay the whole summer in the Willamette. Some are staying the whole winter in the Willamette, and then they're going out from the Willamette rather than from the Mackenzie. So this kind of gives you a little bit of a sense of when fish are really using the Willamette River. And this is an 18-month period. So if we take this group and we move it on over, then you can see that in the winter time through early summer is when the Willamette River is really a critical rearing habitat for these fish. So those are the periods when you would tend to see not only most of your juvenile fish, but you would also see two distinct year classes. You'd see the fry and the fish that have been in there for almost a year. I'm going to move through this fairly quick because what we've attempted to do is sort of diagram all the migratory pathways we found, but it starts getting pretty complicated in a hurry. When we first started, we just sort of said, well, we kind of have two migrant types. We have a yearling smolt and a sub-yearling smolt. And then we decide, well, we do have to add this fall, winter. Some of them do go out, we don't know when. As we've got more information, we have to add a fry migrant. We know those migrate down through the Willamette. And then we start adding in the fish that are migrating and then rearing before they move out. Some in some years, like 2008, when we had good water conditions that extended well into summer, we saw continued migration through the summer. We didn't see as big a drop-off as we normally do. And these fry, some of them are continued to extend their rearing in a Willamette before they go out. Some of the fall migrants are staying in the river. More fish are leaving at different points of time. So pretty soon, when we add like the use of these non-natal streams, we've got a pretty complex diagram of fish moving and rearing in all sorts of habitats. We have a couple minor, what I consider to be minor life history types. We have some fish that actually stay in the spawning areas, and they mature as little males. They can spawn with a returning female, but they've actually completed their whole life cycle up in the spawning areas without going to the ocean. And then recently, we've actually seen some evidence that we have some smolts that may take 2 years before they go. So we have, this large range of diversity of fish rearing and migrating through the system. So in order to support that, because we have fish moving at all times, we have different size groups, it really requires having a whole suite of diverse habitats available to them, and the ability of the fish to actually access those habitats. And this is just a simple schematic of showing how, if you think about it as maybe links in a chain, you want to be able to link habitats from the upstream all the way down to the mouth. And it's not just upstream and downstream, it's also, laterally. As the water goes up, the fish have to have some ability to move out of the, the roaring floodwaters and get some refuge. And then seasonally, the fish have different needs. Their spring habitat needs may be quite different than summer. Summer, they may need a little bit cool water refuge versus spring, which is maybe more for active growth. These are just some examples of the types of winter habitat we can find fish in. They're not that picky. We can go out onto flooded roads and pick up fish out there. I mean, I'm not saying it's their preferred habitat, but they'll take advantage of anything that's available to them. And oftentimes, we kind of wonder, well, what makes good habitat? And this is just one example where, here we have more of a natural beach type habitat with a gradual slope. Here it's a riprap habitat with a steeper slope. And so as if you look at sort of the areas, since fish of these size tend to be sort of edge oriented, they want to kind of stay close to the edge. This area down here is going to be pretty high velocity. And here the fish can kind of choose where they want to be a little bit more. And as the water goes up, you can see that they continue to have access to shallow water habitat, and having some structure in the stream really helps too. Compared to this, as the water goes up, they're still exposed to high velocity habitats, and it's not until the water gets really high before they have some sort of access to maybe refuge floodplain areas. In the upper river particularly, what we think about when we're talking about diverse habitats is creating a more dynamic river system. It's a heck of a lot cheaper to let the river create the habitat than for us to try to engineer it. So this is an area that's just downstream of the McKenzie confluence. It's a real active area. It changes almost every year. And by changing, it creates all these different types of habitats, from shallow water to some deeper pools. This is a little cold water refuge. The water is percolating through this gravel bar, and it comes out here super cold, and fish will draw in there in the summertime. So here's what I want to do here is just show you a series of photos through time in another active area of the river, just to show you how much the river can change. And so one thing to note is this area here is armored. So there's riprap here, there's riprap along this bank. So as we go through this, if you keep an eye on that, you'll see, whether it changes or not. And then this area, all the through here, is not constrained, so it can move around. So here you can see that the river's starting to change a little bit. You had more of a center channel here that's now kind of moved over this way. Within a few years, we're starting to have a channel get cut through here. This channel's being cut off, and more water's going through here. Again, this continues, this keeps opening up. This is almost completely shut off now. This is still a fairly major channel, but gravel's starting to build up in that area there. You can see this gravel ball really developing here and starting to pinch this channel off. And this is now becoming more the main channel here. That sort of pattern continues. This channel's now pretty much cut off, at least at summer flows. In winter flows, this would still provide some good habitat, because it would open up that whole area as the water comes up. And finally, vegetation starting to form in here, and these gravel bars are still forming in this area. So it's possible that this is going to shove the river over here, and it may take on this channel again. And if we just go back then to the original, you can see how much in a little over a decade this section of river has changed. But note that the area up here has not moved at all. It's pretty much constrained by the riprap. So one of the things that we've been looking at is, if we're going to restore the river, we need to kind of tie it into what we've discovered about the life history diversity, and so we kind of considering all of these aspects of it. We want a certain amount of depth and slope. It's good to have the vegetation there. Good to have floodplain access, and this is some schematics showing how much of the channel complexity we've lost through time. And we're hoping that with some more recent activities, maybe we can start at least changing that trajectory back. And nobody's thinking that we're going to get back to these particular configurations, but anything we can do to at least prevent us from going in that direction would be beneficial to fish. So I've been asked before, why does it matter? Some of you have probably seen these schematics of the projected change in temperature with climate change, and it's it's a pretty scary looking graph, regardless of whether this is the optimistic one where we reduce emissions, and this is probably the trajectory we're on now. So with those kind of projected changes, these are kind of the changes we'd expect to see in the system itself, and these are the effects that it could have. We could see loss of complexity. We could have constrained periods of time when fish can actually physically migrate. Disease increases, and the spread of some of the non-native species that we have in the river. So having the diverse life history that we still have, gives us, I think, some measure of optimism that these fish are still able to sort of spread the risk. So, their period of fry migration is still pretty long. We've got two distinct smolting life histories. So fish can go out in their first year, or they can go out in their second year. And so one example is, suppose in this second year we enter into the second summer, we enter into some really poor water conditions, a drought. Well, having the sub-yearling smolt group, most of them will have gone out by the time, say, a drought condition really hit hard. So that group potentially would then have some advantage. They'd be out of the freshwater and in the ocean, and therefore you've kind of spread the risk of, you don't have everything constrained down to, say, one life history. And it's the same in the ocean, since sub-yearlings are hitting the ocean a year earlier than the yearlings are. And if, for example, in this first year you had poor ocean conditions, and you still have your yearlings in freshwater, they haven't entered the ocean yet, and so hopefully they'd be able to pick up the slack. And we do tend to see some of that not only across basins. Here we have an example of the contribution back to the adult returns of the sub-yearling smolts and the yearling smolts. The sandy yams tend to be a little heavier towards the sub-yearlings, and that part of that may be a reflection of the influence of dams. But even within a single basin, we see quite a range of variation in the contribution. In some years, the sub-yearlings really didn't contribute that much to the adult returns. But in another year, they contributed over half of the adult returns, had that sub-yearling life history. So this again sort of spreads the risk, and it also provides some sort of stability to the population. You're not relying on just a single life history to pull the load. So I saw this quote in a documentary recently that I thought was pretty interesting. We often think of progress as being, you just charge ahead. It's economic growth. If it's not a certain percentage, then things are bad. If housing starts aren't continually increasing, then that's not progress. But if you're heading towards a cliff, is it really progress to just keep charging forward full steam ahead? Or is it progress, as Doug Thompson said, to actually turn around and take a step forward? And that, that's, again, societal choices will have to be, made. And in some cases, compromise might not actually be, the best, solution. This is a pretty interesting example of, well, maybe it'll only fall halfway because, you're kind of figuring that, well, it's somewhere in the middle. It can't be one or the other. So one of the things, go ahead, is I've been asked before, am I optimistic that we can recover Chinook? And most times I'll say yes. I mean, most days I'm still optimistic, and there's several reasons for that. If you really think about what Chinook have been through geologically, I mean, they've withstood volcanoes, the Missoula floods. So far, they've withstood humans. It's kind of ironic that we're in the same category as these, or maybe even exceeding them. But and I think that if we take some bold actions, that the fish do respond, and we've seen that time and time again. Oftentimes, it's sort of like you're just you're taking your foot off their throat, even just a little bit, and they'll respond. And we have seen for example, in the Willamette, in up and down, really the whole basin, especially with some of the work the watershed councils are doing. I mean, we have seen a lot of ongoing and planned, conservation and restoration actions. So, I think that the trajectory of not only the actions but the involvement of citizens has increased. Certainly, since I've started working. It's much higher than it was when I first started. And I just want to put this up. That our main contact now is Luke. So any questions you can direct to Luke, and he'll answer them all. And I guess finally the other reason for optimism is that in the end, actually rivers will end up winning. This is the '96 flood, which everyone thought was like this really major event. When you look at it historically, the '96 flood is pretty low on the scale of historic flood conditions. So we sort of think that because we have these dams that we kind of live this nice protected life, but that's sort of a false hope, I think, in the long run.
I've seen par in some low when the in the river when the river levels drop during every day. I've seen par. It's trapped in pools. Are they at any danger when that happens?
Well, yeah, they would be if the water doesn't come back up again.
Okay, so
Yeah.
so regular just tidal influence doesn't affect them.
Yeah, if as long as it's not a pool that's extremely warm, and usually what we've seen is that fish can move in to some pretty big areas that when you look at it you think, well, they shouldn't really be in there, but then you go back and they're gone. Oh. So they can, I think, respond fairly quickly to some pretty small changes in probably in either flow, current going through that particular area, or change in water depth. But certainly there are areas where they could get trapped.
Well, I'm just talking about the regular tidal influence in the
Yeah,
Willamette.
those generally, I think the fish can kind of hang on.
Hang on for those 8 hours or whatever.
Yeah.
Thanks.
But the trapping part is one thing that we've worried about when, for example, proposals are made to open up gravel pits, for example. Because sometimes it's like the proposals to dig a trench and let part of the river go into this gravel pit, which oftentimes is steep-sided, so it's not that great a habitat to begin with. But then sometimes there's not that much consideration for how the fish would actually get back out. So those sort of off-channel restorations need to consider both the ability for fish to get in and get out in a reasonable time.
Thanks very much. My name is Dick Springer. I'm the manager of the West Multnomah Soil and Water Conservation District. And our areas in the lower Willamette River, particularly Multnomah Channel, Sauvie Island. So I'm kind of curious about the tidally influenced floodplain areas and wetlands in terms of, I've seen high water and I've seen flood waters too have a real impact. We hear a lot about off-channel refugia for the migratory species, not just Chinook, coho, obviously,
Right.
various times of the year. And I know the edge effect in terms of, food chain and feeding habits, I suppose, at various times. Can you shed a little light in terms of what's happening or what you see in that area as far as opportunities? We have the Portland Harbor is kind of a mess, in terms of, the loss of natural habitat there, and that's about 10 miles that every fish going up the Willamette River has got to get through the Portland Harbor, we know. So any thoughts about that in terms of the migratory for the juvenile salmonids?
Yeah, you mean in particular the Sauvie Island area? Or?
Well, I'm thinking of Multnomah Channel, and
Right.
again, some of those floodplain lakes, and those tidally
Smith and
influenced
Bybee.
wetland areas.
Yeah, Luke's involved in some sampling in conjunction with NOAA Fisheries down in that area to try and shed a little more light on fish use. I think for, say this Portland area, we're not going to have, a whole corridor of native natural habitat. I think it's important if we can have pockets of habitat for fish to move down. Some work that Tom Friesen did in the 90s, did indicate that through this lower Willamette, the fish were not only spending time, but they were putting on growth as they were moving through. So it's not, it's not like a complete wasteland that we should be flushing fish through. On the other hand, any chance we get to either conserve or restore sort of more of a natural riverbank, like for example, that the example I gave with the shallow water habitats, any time that you can achieve that is going to be beneficial. And even if you have like a pocket here and a pocket here, and just sort of these, chains of habitat, sort of habitat patches in a way, that's probably the best we can hope for here. And then when you get down to the mouth, having that Sauvie Island area, I think, may provide a pretty big refuge, particularly if you had, say, a pretty high flood event where the patches you have upstream are not that big and the fish might get sort of flushed through there. If they reach that more of a, what used to be a big delta area for refuge, then, then that would certainly, be beneficial. And we know that fry and some, smolts use that based on other studies.
I guess the slide that caught my attention as much as any of I don't remember the names of the two streams, but 15 miles up and 4 miles up,
yeah.
where you did find, was it fry or smolt? Fry.
Actually, I don't know in those particular cases, but we have found both fry and larger.
Any information is, and you mentioned that they were able to use passages. They were able to. Is there any information about the dimensions, the length, the size of the culverts that allowed for passages compared to maybe those that didn't? We're going to have a lot of upstream culverts. We're picking away at the lower stream culverts, but we're going to have a lot of private culverts upstream that I don't know will ever be able to. Is there any sense of what will work and what won't work in that scenario?
Yeah, there are some, fish passage guidelines. I don't know the specs, specifications off the top of my head, but in the case of those streams, I would say I'm familiar with some of them. The culverts weren't particularly stellar, but probably the thing it had going for them was it's fairly low gradient, and so even if they were fairly long, the fact that the fish didn't have to go up, kind of a high gradient stretch, probably allowed them to have access to the areas on the other side of it.
Thanks.
So I think velocity is probably a big one, especially if you're talking about fry.
There was that one fish that swam into the mouth of the triangle.
Pardon?
One of our fish that we had tagged swam into the mouth of the triangle.
Yeah,
last
I would
summer.
think so.
So
Yeah.
we got
Above or
that
below
was
the culvert?
well, it was pretty
Close
close
to
to
the
the mouth.
Yeah.
It was pretty close to the
Down
mouth.
in the-
I think we got two captured in the last 10 years or 5 years above the culvert, but
Yeah, but more than that, about 3 per year.
yeah.
Good notion of not a run.
Oh, thanks. And I guess that was one of my questions is the gradient of those streams down by Corvallis was quite a bit less than a stream like this.
Mm-hmm.
So I guess I have a question as to how much they would use because this is also historically maybe it wasn't so flashy because you didn't have all this hard surface up above, but now it's pretty flashy. So when you're going to have some higher water events in the Willamette, potentially you're going to have some pretty flashy conditions up here.
Mm-hmm.
I don't know if that's a comment or just as much of a question as whether there's potential with doing some, continuing to put large woody debris in the stream to release some of that velocity and then of course reduce the culvert if we still have potential for bringing some of these up this stream.
Yeah, I'm not that familiar with this stream, but my guess is when you get into these smaller high gradient streams, they're probably used more by cutthroat trout and potentially coho, at least in lower gradient stretches. I think for the juvenile Chinook that are migrating from upstream, I think the important areas tend to be down around the mouth and confluence of these streams. We've seen that in, when we've been sampling for fry, for example, we've seen big concentrations of fry at the mouth of the Tualatin. And we're pretty sure there's not a big run of spring Chinook in the Tualatin. I can't say for sure there's none in there, but probably not enough to have that large a concentration of fry. But when you look at the river, that tends to be sort of a natural, fairly large eddy that fish would tend to pull into. And same with the mouth of the Molalla, for example. And the Molalla does have spring Chinook in there, but when we sampled upstream of the mouth, and actually we went up quite high, we didn't find another Chinook. They were all clustered at the mouth, so we were pretty confident they're also coming from upstream. So those areas, because now you're out of the high gradient stretches and kind of down at least into some sort of a lower gradient and a little flatter stretch. Those I think are areas that the more you can say extend the length of those along the stretch of a river, then the better off that would be for rearing. I think I look at some urban stream restorations, and I have to sort of weigh, how much money, if you look at the expenditure of money, it's like, okay, if we spend this much on a small urban stream, is there really a better use for that money, somewhere else, where for that amount of money, maybe you can actually secure, several miles of riverfront,
sure,
for example. So I think, and it's kind of hard to do at the watershed council level individually, because you're focused on a watershed, and that's likely where OWEB comes into play. Is they have to sort of evaluate all these proposals and say which one do we think is going to give us the biggest bang for the buck.
Exactly. All right. Thanks. Anybody else want the talking stick?
I sort of have an interest in urban nature conservancy, so I do think of, once the fish get past Oaks Bottom is kind of a super highway with not a lot of roadside attractions. But you indicate there can be, should be pockets of good Chinook habitat. Where are they? What might they look like? How can we create them in the area, say Selwood Bridge downstream?
Yeah, I think those, there's two sort of approaches. One is you're opportunistic. If you can find somebody who's willing to do the work, you jump on it. The other is, for example, upriver, we've been working with OSU and some U of O scientists to try to identify areas that we've modeled, say, a 2-year flood event, and then we look at a map and we say, okay, in this 2-year flood event, here's areas that potentially could act as floodplain habitat, but maybe there's an area that it's blocked off because of a revetment. So those are areas where you look at it and go, well, if we could get the money or the opportunity, that would be a revetment that would be a high priority to remove, because it opens up, like say 20 acres of floodplain habitat. So there may be some, tools that could be similarly used down here, where you just, you'd look at the entire, say, stretch of river where you think habitat's real limiting, and see if there's any, little pockets of either natural type habitat or at least areas that aren't along a seawall, and say, if we get the chance, can we do something there? There's probably some stretches where it's just not going to be possible, and so we hope that maybe having enough area upstream and downstream of that will be, sufficient, and the fish are just going to have to kind of, bomb through the nuclear zone, so to speak.
Anything being done at Ross Island?
I've sort of lost track of that. I know that at one point it was kind of on a trajectory to that they were going to try to fill in some of the excavated area to make a more shallow habitat. The last I can remember hearing is there was disagreement on what you used to fill in that, that shallow habitat. So I'm not sure how far along it's gotten yet, but that's certainly a potential area where if you can actually create something that has shallower water instead of real steep sided, that's a really good area for restoration.
As far as the upper river dams, I know the hatcheries, I guess, were assumed to take care of restoring some of the, certainly not the native, but some of the fisheries. But has there been a serious look at trying to provide fish ladders or any way to, they're talking about trying to restore salmon above the Grand Coulee. If they're talking about that, I mean, we got to be talking about other options for the upper Willamette. Is that getting any serious consideration in terms of trying to get them over those dams and back down?
Yeah, there's a really large component of the Corps of Engineers biological opinion that's focused on figuring out ways to move salmon above the dams and to get the juveniles downstream. At this point, the most likely scenario is going to be to, as they're doing in Cougar, is to, they built an adult trap, and so they'll truck the fish upstream. The challenge on a lot of these is not so much getting the adults up, it's getting the juveniles downstream. And I probably am not, a big fan of the Corps, but we've basically, with this work, we've complicated their lives because we've demonstrated how diverse all the migratory pathways are, and that makes it real difficult to figure out how to accommodate a natural expression if you've got fish above a dam, and you're trying to get fish downstream maybe at the same time that they're filling the reservoirs, which makes it extremely difficult to get the fish down. So so that's going to be a huge challenge, and really expensive. But what we've, and I think actually in the long run we're going to need to do something, because we can't rely, in a place like, say, the North and South Sandy Dam, you can't rely on the sort of remnant habitat that's below the dam to rebuild runs, because it's down in the last maybe 20% of where they historically were, plus it's affected by water temperature releases from the dam and then altered flow conditions below the dam. So it's already been impacted multiple ways. So we'll have to get fish above, and maybe, for example, at Detroit Dam, I don't know if you folks are familiar with the Pelton Round Butte on the Deschutes, where they built a massive, they built a massive tower to not only change the water temperature that's being released from the reservoirs, but also to collect juveniles going downstream and get them downstream. So that may be what it takes. I've personally advocated, and actually did this in front of the Corps, that we start looking at removing a dam or two. And one of the most obvious ones to me is Lookout Point Dam on the middle fork of the Willamette, because it's really low in the system, and the area above there is actually still in really good shape. There's a lot of Forest Service land up there. And you wouldn't necessarily have to remove the entire dam. You could still use it to capture maybe the biggest flood pulses, but you'd let them go, fairly quickly. So I was asked how you would do that, and I said, well, I'm not an engineer, but with a couple sticks of dynamite, I could probably put a hole in the dam, and then you could put a big plug in there when you need it. Yeah. Yeah.
Elwha Dam? Yeah.
Yeah. Yeah.
We're talking about the Klamath River dams.
Mm-hmm. Yeah.
Bringing it down the run of the river to get
Yeah. So in this basin, our dams are not providing a huge amount of power. In terms of the regional grid, it's something like maybe, I think it's less than 10%. So that's not, the dams really were built for flood control. And I think you could modify them so you could still maintain that primary purpose. It's just you wouldn't be storing a lot of water for a long period of time.
Thank you.
Well,
I just have one real quick question. Did I hear correctly that this was going to be a very large spring run?
This year? Yeah, I think
And
it's supposed
why
to
is
be.
that?
Huh?
Why is that exactly?
Oh, it's,
complicated.
we always just point to the ocean and say, well,
Oh,
ocean conditions.
It's the currents, the conditions, yeah.
I mean, if I was, a better administrator, I would say that we should take credit for it, for all the good stuff we've been doing. But then, when the runs go down, then you're sort of left with egg on your face. So.
Thank you.
Mm-hmm.
well, thank you. Let's give them a round of applause. Indeed.
I got to keep this, right?
And thank you all for turning out. Really appreciate Kurt and Luke coming up and taking over, as you say. And we're, of course, been working for a long time here doing upslope restoration as well as some in-stream work, as well as some other properties up on Tasavia Island. We're looking to do something up there. Up on the Clackamas, we're trying to put some additional side channels in up there on some of the state park property. And so really appreciate the support, the Watershed Council, the Friends, West Multnomah, and the rest of you that we continue to work and bring the fish back. So thank you much.